Okay. So Gibbs energy of mixing's important because you want to see if two things will mix or not. We're going to utilize this. When it comes to changes in physical state, it's important. Also, when we consider reactions, chemical reactions, this Gibbs energy is important because it's related to K and if the process will happen. The entropy of mixing might be something you want to consider because, whoops, the Gibbs energy is made of enthalpy and entropy, basically, right? So you can measure enthalpy really easy. Entropy can tell you a little bit more about what's happening in the system. So we have shown that if you take the change in Gibbs divided by temperature, keeping pressure and moles constant, that's equal to negative S. So let's say we wanted to relate this to S of mixing. What would we take the derivative of? To get delta S mixing. Change in what? Yep, G mix. With respect to what? Yep, temperature. And what are we holding constant? Yep, pressure in moles. Okay, if we manipulate this around, get delta S of mixing the negative of that, right? We can plug in with our expression that we recently just solved for, where we want, we'll utilize this one. That was good. Okay, what are we going to get out there? So this is our expression for G of mixing, right? To get to S, what do we got to take the derivative with respect to? Yep. So what's going to happen? Yeah, temperature disappears. We're just left over with negative chi A right? So now we know about the entropy of mixing. Is entropy favorable? Isn't it? Because it's a constant battle between enthalpy and entropy to make sure if something will happen spontaneously or not, right? Okay. So on the daily problem, if I ask you figure out G of mixing and then I say find S of mixing, shouldn't be too tough to find it, right? Okay. How we doing?